Hello, and welcome to lesson 8F on natural logarithms and applications. We've already learned about the common logarithm, which has a base of 10. And typically, these logarithms don't include the base. So log of x means log base 10 of x. Natural logarithms are pretty similar. They're frequently used to describe natural events, and they're used when compounding continuously. The logarithm has a base of e. E is an irrational constant like pi. It's found a lot in nature. It's a naturally occurring constant that we see over and over and over again, like pi. And it is equal to about 2.7183. And the notation log base e of x is usually abbreviated to ln of x. That's how often we see this, guys, that we made an abbreviation for something that was already pretty short, ln of x. So whenever you see ln of x, that really means log base e of x. And it works just like it is a logarithm, so it works just like a logarithm. Natural log of 31.5 equals 3.45. I want to rewrite that in exponential form. That's really e to the 3.45 equals 31.5. Similarly, natural log of 3 equals 1.009 is e to the 1.009 is about equal to 3. We can also switch from exponential form into logarithmic form. E to the 4th equals that. That would be the natural log of 54.598 is equal to 4. And e to the 1/3 equals 1.396 would be the natural log of 1.396 is equal to 1/3. Notice we don't even need the e because we're using that natural log symbol. Now I want to express these as a single logarithm. You guys have been doing this with normal logs. This is the exact same concept. I'm first going to pull that 3 in there. So I have natural log of 2 cubed plus natural log of 6. That's really the natural log of 8 plus the natural log of 6. At this point, I can combine those with multiplication. So I get the natural log 6 times 8 is 48. So the natural log of 48. Do the same thing here, pull that in there, so I get the natural log of 3 squared minus the natural log of 5, or the natural log of 9 minus the natural log of 5. Use division, it's the natural log of 9/5. So let's now work on solving some of these. Just like when we were doing normal logs, we set these equal to x, so I would then flip it into exponential form. I get e to the x equals e, because my base here is e. Well, there's a hidden 1 there, therefore x equals 1. Same thing here, there's a base here of e, so I get, set it equal to x, e to the x equals e squared, therefore x must equal 2. Now if you look, we could also think about the fact that if we've got an exponent here, we learned we can pull the exponent to the front of anything, where this would become 3 times the natural log of e. And the natural log of e, because it's e to the e, right? It's over here, this number 7, that's equal to 1. So really the answer here is just 3. So here I can pull that 8 to the front. That's 8 times the natural log of e. The natural log of e is 1, so I just get 8. Or we could do it by setting it equal to x. There's 2 ways to go about this, guys. Again, there's a hidden base of e here, so I get e to the x equals e square root of e. Well, square root of e is e to the 1/2. So therefore, x must equal 1/2. That's the value of that logarithm. Set this guy equal to x. I get e to the x equals 1. The only way to get 1 over here is to raise that e to a 0. So therefore, x must be 0. Here we set that equal to x. I get e to the x equals 1 over e cubed. Working that guy out, I'm going to rewrite them both with the base of e. That's e to the -3. Therefore, x must be -3. Same thing here. Set that equal to x. I get e to the x equals the cube root of e squared. So rewrite that as an exponent. E to the x equals e to the 2/3. Therefore, x must be 2/3. And one last time, set that equal to x, my bad. E to the x equals 0. There is no way to do that, so this is undefined. We can't do that. Undefined. So we can actually make a generalized statement that the natural log of e to the p is just equal to p, because it's just equal to the exponent. Now let's hop into the calculator and take a look at something. Evaluate the natural log of 3 on your calculator. So when we come over here to the calculator, you'll see there is an e to the x button right over there. It's under a natural log button. Oh my goodness, we're going to use that a lot. So let me add a calculator. If I do e to the third power, I get an ugly decimal. And I'm sorry, guys, you're not catching all that, are you? I get this ugly decimal, and that's okay. So coming back over here, we actually can use the calculator to help us solve these. The way we do this is we isolate the exponential expressions, so it's already isolated here. Then we take the log of both sides of the equation. It's often more efficient to use the natural log instead of the log. So when using ln, remember that the natural log of e to the x is just equal to x. So here I'm going to take the natural log of e to the x, do it to both sides, natural log of 3.1, which means this just becomes x equals the natural log of 3.1. And at this point, I jump into the calculator. I go, the natural log button's in blue right there, control natural log 3.1, hit enter. I get 1.1314. So x is about 1.1314. And I keep saying about because e is one of those non-terminating decimals. So everything we're doing here is really an approximation and not an exact answer once you put it in the calculator. So here I'm again going to take the natural log of both sides. Natural log of e to the 2x minus 3 equals the natural log of 5.7. At this point, the exponent hops out. 2x minus 3, and the natural log of e disappears. Equals the natural log of 5.7. I'm going to add 3 to both sides. I get 2x equals the natural log of 5.7. I'm going to put that in parentheses. Plus 3, and then divide everything through by 2. I get x equals, give me more space to write, please, the natural log of 5.7 plus 3 all over 2, being really careful with your grouping here because that 3 is outside the natural log. So we're going to jump into our calculator. I'm going to pull up a fraction bar, and I'm going to do the natural log of 5.7. I'm going to come outside of that to do plus 3, come down to do divided by 2. And we get 2.37 and then some. So x is approximately 2.37 and then some. All right, keep going. Let's do the natural log of x equals 5. This guy, I want to get the x by itself. It's already in a natural log. The easiest way to get it out of a natural log is to switch it into exponential function, into an exponential format. So this becomes e to the 5th equals x. Well, I can solve that in the calculator. Come over here, control e, nope, not what I want. E to the 5th, and I get 148.413. That's my answer. 148.413 is approximately my value of x. And again, here it's easier to switch into exponential form at this point. So I get e to the 1.5 equals 2x minus 5. Add the 5 over. E to the 1.5 plus 5 equals 2x. Divide by 2. E to the 1.5 plus 5 all over 2 equals x. I'm going to hop into my calculator and plug that in. Over here, I'm going to call up a fraction bar, and I'm going to do e to the 1.5, get outside of the exponent, plus 5, all divided by 2, and I get 4.74 and then some. So x is approximately 4.74. Now again, the greatest use of E is in real-world application problems because it occurs so often. Here's an example. The population size y, the community of lemmings, varies according to the relationship y equals y naught e to the 0.15 t. In this formula, t is time in months, and y naught is the original population at t equals 0. So estimate the population after 6 months, that's my t, If there were originally, that's originally 5,000 lemmings, that's y naught. So we just simply plug in. Y equals 5,000 e to the 0.15 times 6. We just plug that in, 5,000 e to the 0.15 times 6. Come over here, 5,000 times e to the 0.15, still in the exponent, times 6. And we get, oh, there's an, you guys can't see this, there is an E7, meaning that it's actually, did I do this right? Give me a hot second, guys. Yes, I did do it right. Okay. We get such a large number that it's gone into scientific notation on my calculator. 4.05154 E7. So y equals, did I come back? That doesn't, I made a mistake up here. You see that, guys? It was 0.15, not 1.5. That'll make a huge difference on your answer. Come on. Let's change that, shall we? And put our decimal there. Knew I made a mistake. There we go. 122.98. That makes a heck of a lot more sense. 122.98 lemmings is our approximation. Now, after how many months will there be? 3,000 lemmings. So now t is my missing value. So I have 30,000 is my new y equals, we still have your 5,000 over here. And then e to the 0.15, the t is now what's missing. I'm going to divide both sides by 5,000. And when I do 30,000 divided by 5,000, 1,000 divided by 5,000, we get 6. Beautiful. Oop, wrong thing. So I have 6 equals e to the 0.15 t. I'm going to take the natural log of both sides to isolate the t. So it's the natural log of 6 equals the natural log of e to the 0.15 t, which means that 0.15 t can come out of the exponent. I get 0.15 t equals the natural log of 6. I want to get the t by itself, so divide by 0.5. I get t equals the natural log of 6 divided by 0.15. That goes in your calculator. We do the natural log of 6, parentheses, divided by 0.15, and we get 11.945, coming back over here, which is about 11.945 months. It's really about 12 months if we were going to round that, but anyway. All right, the formula W equals 0.00185 h to the 2.67 is used to estimate the normal weight W of a boy 8 inches tall. Find the expected weight of a boy who is 43 inches tall. So we have a height already, and I just want to find his weight. This is a plug and chug problem. W equals 0.00185 times 43 to the 2.67. Simply plug that in the calculator. I plug it in, I hit enter, and I get 42.514. So he is approximately 42.5. What is our units? Just says weight. I don't like that. Units. Okay, now, oh, there it is, pounds. Boom, pounds. Now find the expected height of a boy who weighs 140 pounds. So we know the weight, that's 140, equals 0.00185 h to the 2.67. I'm going to divide both sides by 0.00185. Went ahead and did that in the calculator, and now I've got something raised to a power. I am going to take a really weird radical, guys. I'm going to take radical 2.67 of both sides. I'm going to do radical, please work, of 2.67, and same thing over here, radical 2.67. Now I'm keeping that number stored in my calculator that I found before. So I go over here and I want to go control. I want the nth root of 2. Come on, do as you're told. Delete. 2.67. And I want to come in here, and when I do that, I now arrow up and hit enter, and it's going to drop that whole number in there for me. And I hit enter again, and it gives me 67.193. So we come back over here and we get that H is approximately 67.193 inches. All right, moving right along. Lots of calculator tricks in this one. Now, the greatest use of I think this whole unit is in interest. So there's two types of interest. There's compound interest and continuous interest. Compound interest is interest that's taken at certain points along a timeline. So A is the amount accrued or owed, so that's the current amount. P is the principal invested, that's where you started. R is your annual interest rate. T is the number of time in years, and N is the number of compounding periods per year. So let's do an example with this. How long does it take for an investment of $3,000 to double? So $3,000 is my principal, that's where I start. Double means you'd then be at $6,000. That's going to be your accrued. That's where you want to end up. If it is invested at 7%, that's 0.07. That's going to be your rate. We always use decimals. We never use percentages. Compounded monthly. That means we are compounding. N is my number of times I'm compounding a year. If I'm compounding monthly, I'm compounding 12 times. And then round to the nearest year. So the thing I'm missing is T. So we plug in. We get 6,000 equals 3,000 times 1 plus the rate is 0.07 over 12 to the 12t. Now I'm going to divide both sides by the 3,000 to get 2 equals 1 plus 0.07 over 12 to the 12t. I need to get the t's in the exponent, so the way to get rid of it is to take the the log of both sides or the natural log of both sides. I'm going to use natural log because it's a shorter hand, but it really doesn't matter which one you choose. You're still going to end up with something really ugly at the end. So now I have the natural log of 2 equals, when I take the natural log, that 12t can come to the front. 12t times the natural log of this hideous thing, 1 plus 0.07 over 12. Now I still want to get the t by itself, which means I divide off everything that is not t. I divide by the 12, I divide by the natural log of 1 plus 0.07 over 12, and I do that on both sides. 12 times the natural log of 1 plus 0.07 over 12, that's a handful. And then this thing is what goes in the calculator. So we hop over to the calculator. I'm going to get a big fraction bar because this thing is ugly. We have the natural log of 2 over, down, thank you, 12 times the natural log again of 1 plus 0.07 divided by 12. And when I do that, I should get my answer of 9.93096. Come back over here, I get 9.93096 is approximately equal to t. It tells me to round to the nearest year, so it's approximately 10 years is my answer. It's ugly math, but it works. Compound interest is similar continuous compound interest is similar to compounding interest, except that you are continuously compounding, and therefore we have a new formula for that, and that is A equals PE to the RT, or A equals PERT. R is still your annual interest rate, T is still your time in years, P is your principal, your initial investment, and A is your amount accrued or owed. That's where you are today. E is the constant, E. It is not a variable, it is actually a number. So let's look at this. Invest $3,000 account paying 5% annual interest compounding continually. How much will you have in 4 years? So 3,000 is my P, that's where I start. 0.05, that's my rate. And I want to know how much I'll have in 4 years, that is my T. And we're trying to find how much I want to have, that's my current value, that I'm trying to find A. This is a plug and chug problem. A equals 3,000 times e to the 0.05 times 4. That goes straight in the calculator. We jump over here, we do 3,000 times e to the 0.05 times 4. We hit enter, and we got a negative, because I did natural log. You know what, guys? It's a bad day. 3,000, please work, times e to the 0.05 times 4. Enter. And we get 3,664.21. So A equals $3,664.21. That's how much you have accrued. How long would it take? Would you have to wait to have more than $4,000? Well, we simply plug in $4,000 for A equals 3,000 times e to the 0.05, and the thing that's missing now is my time. So I divide by the 3,000, this becomes 4/3 equals e to the 0.05 t. Take the natural log of both sides, I get natural log of 4/3 equals, when I take the natural log of e to the 0.05 t, that just becomes 0.05 t, and then divide by 0.05 on both sides. I really prefer this continuous over the compounding because it's so much simpler. So when I do that, I hop back in the calculator. I am this time going to do the natural log of 4/3. Why is this not picking up my keystrokes? Sorry, guys. 4/3 divided by 0.05. Hit enter. And we get 5.753. Come back over here. 5.753 is about equal to t. So you'd have to wait about 6 years if you're rounding to the nearest year to get to that point. Okay, so now the next two, I actually want you guys to try. I'll talk you through choosing the appropriate formula, but then I want you two to do these, or you guys to do these problems. How long will it take for an investment of $500 to triple if it is invested at 5.5% compounded quarterly? Because it tells you compounded quarterly, you're going to use your A equals P times 1 plus R over N to the NT formula. Okay, that's the formula you're going to use on this guy. Whereas down here, how long would it take for investment of $5,000 to triple if it is invested at 5.5% interest compounded continually? That means you're going to use your continuous interest formula, A equals P e to the RT. So guys, go ahead now and try these two problems on your own. All right, guys, go ahead and check your answer. And you know what? We're going to leave this guy here for class. He's going to be classwork. All right, guys, thank you so much, and we will talk again later. Good job.